Hello everyone, welcome to part first of LLM Jargons Explained. In this video, I'll be discussing about how a decoder works on a high level. In my previous video, we have discussed about how an encoder works in detail. Please feel free to check the video and come back to this to gain more understanding of how a decoder works. So when it comes to decoder, there are two kinds of models. One is decoder only model and second one is encoder decoder only model. The explanation I'm going to give now, it is 90% of the decoder only model, and I will also give a brief of how a decoder model in the encoder decoder architecture works. And while we were discussing about encoder only model, we have discussed detail that each of the encoder blocks, how it looks like, how many heads each of the encoder block have, and how many blocks, or we can also call it as layers, how it works, and self attention, etc. So here as well in this part, we will be going through the certain parts of it. There is a subtle difference between how a block in decoder works differently from how a block in encoder works. We will look into all those details. So I'll be taking one head and of one layer to give some explanation of how a decoder block works. Okay, now let's take some example here. Let's say the input is something like I love my dash, right? In the sense, it could be anything. I love my country, or I love my nation, or I love my world. It could have been anything. And in the decoder block, like typically whatever we get it in GPT models, the GPT-4 or even ChatGPT or nowadays Gemini, Bard, whatever those models are, here whatever I love my, this is what we call it as prompt, and whatever the answers we get, that is what it called generation. And decode for any model, whatever we input, that will act as an, what are typically we call it as a prompt, that will act as an input to the model. And I'll not be discussing about how a ChatGPT works on a high level. That will be discussing in a separate video. But how a typical decoder model will work, that's what we'll be discussing. In short, ChatGPT kind of a model will follow mainly two methodologies. One is pre-training, and second is something called SFT training. So in this video, I'll be talking about how a typically pre-training will be done, especially how a decoder model will work when it comes to pre-training. Okay. And let's say the I love my is the input. Let's see how a decoder block will try to generate the next word. Okay. And just like we have seen in encoders, where each of the token or the word subword that depends on underlying tokenizer will be projecting through the weight matrix, in this case query matrix, key matrix, and also weight value matrix, and we will get accordingly q, k, v vectors, right? Similarly here in this example, I have taken like I love my, and we have got correspondingly q, k, v vectors. So one of the things in decoders which has made mainly a differentiating factor from the encoder is something called mass self-attention, right? As you can see here, so far we can able to see only first three words, and we will not able to see the next word till we generate. That's why in the training data set, whatever the attention we try to get for a given word, it will always be on the attention of the words so far the model has seen. For example, let's take in the training data set, I think we are just processing this. Oops, just give me a moment. Yeah, for example, we will discuss about this anyway. So example, let's say we are processing the word love, right? And in the training data set, we will be able to see only the word I, and the word my will be hidden, though it is a part of our training data set. Okay, and that is what we call it as a masked self attention. Okay, so literally the my or whatever the other words in the next, this word will not able to see it. Similarly, for the word my, only I and the love word it will be seeing, and none of the words after the my words it will not be seeing. So far, in simply put, whatever the words processed so far, only those words will be taken into consideration while calculating the attention. And it is also called mass attention. In PyTorch, if you are using a torch, there is something functionality called TRILE, that is means lower triangular, using which implementation of this self attention is much more easier. And we'll see how else we can deal with that down the line. So once we have QKV vectors, and this will be passed through a typical masked self-attention. I have taken this attention here, but I think in this decoder, it is like a masked self-attention for the reason I just explained. And it will be going through multiple layers in GPTs and all. I think we have like 96 layers or 90 plus. It's humongous. Okay. And what it is being done is internally, because this is the word, I think this is the last word, right? Or the token, you can call it as. We will take the query, because this is, we need to predict what is the next token given the previous tokens, right? And we will take the query of the my, and we will be calculating how much importance this word needs to give it to the I word, and how much this word, that is my word, has to give the importance to the word love, by doing q into the key values of the respective words. In this case, q of my will be multiplied with k of I. Similarly, q of my will be multiplied with k of love, and so on and so forth, right? And that's what we call it as q into k, and we will be divided by the scaling factor. I found one of the interesting thing how the scaling factor works. We will definitely discuss about. I found it in Andrew Karpathy's video. I think if you are interested in why there is a square root, why not something else, I think you should definitely check it out. But I will try to explain in short at the end of this video too. Then we will typically multiply with by how just a typical encoder works. Then the things will move on, right? And after finally, we also have a softmax layer. And softmax layer, as I was telling in the starting, it might predict country, or it might predict nation, or I love my family, or whatever it is. Let's say in our training data set it is something like I love my family, and let's say we have country, and which is not the correct, right? According to our training data set, then the back propagation will happen. Let's say in a training data set itself, the country will be there, and then in that case there will be loss will absolutely zero, right? And so that will not be back propagated. And let's say now we have taken, let's assume that country is the one which has got topmost probabilities. That's what softmax done. It will give the probability for each of the generated tokens of the outputs. And I love my, we take the country. Again, similar process will be followed for the country as well. That means, because what will be the next immediately token after to the country? That's what the question. Again, QKV will be generated for the variable country which was generated in the previous step, and query of the country will be taken, multiplied with key values of the previous words, in this case I love mine, and a similar methodology will be followed. So this will keep on following until we generate end of the token. Each of the model will generate a special token, and until we reach the end of the token, or each of the model also comes up with something called context window. Either we run out of this, we will keep on generating those. Okay. And typically, whatever the prompts you have given for this, for example, I love my, right, this is the input I have given. And for example, love, we need not calculate what is the next word, because that is already given in the prompt. We need not predict what is next to the love word, right? So all these the prompt tokens can be processed parallelly. That's what in the industrial world it is also called as pre-filling. And all these words, you all these tokens which are given in the prompts are executed parallelly or computed parallelly using GPUs. And whatever the next generation tokens we get, those are all based on iterations. In this example, we have seen, okay, I love my, we have that as the input. We could able to generate country as the output. And again, country needs to be input to the next. Again, we will get something, right? I love my country, comma, something, and keeps on going on, right? So that is an iterative process, which is a bit slower than the pre-filling phase. And this is called a pre-filling, and this is called a decoding. These concepts will help us understanding the future LLM jargons when we especially discuss about how a KV cache or the page attention works, and how pre-filling and decoding acts as a major concepts in understanding these sub concepts, you can say. um, in this, I think there is also some topic called teacher forcing. For example, let's say in your training methodology, let's say you have in, let's say the training sentence goes something like this, right? I love my nation, or I love my country. So typically, what you'll do is you will pass the I word, and whatever the predicted tokens out of the attention in the training dataset, you will try to give it to the next token. And whatever the second iteration, whatever the token generated in second iteration, you will try to give it to the third, and so on. But initially, when you try to train a model, by default, all the weights, attention weights, or your feed forward networks, or your layer normalization, everything will be randomly initialized. And when you try to generate a token, it will be so random. And for example, for I, it could be generating something random, which might be far away from the word love, and that will act as a second iteration, right? To avoid this, of course, you can also go ahead with that. Just that number of epochs to train your model will be too much, and that will be computationally heavy. So there will be something called teacher forcing, the methodology will be using. And for example, I, we have given the I as a token to the decoder model, and whatever is generated, that will be used for back propagation. But for the next iteration, instead of giving the generated token from the previous iteration, we will be giving the token which is in the training data set. Okay. And this is the methodology. It is usually called teacher forcing. Similarly, if it will keep on happening, typically it is taken for 3 epochs. After 3 epochs, this enforcing of the training tokens in the during training methodology, that will be stopped. And from the fourth epochs, I'm just taking, this is not a strict rule, just a rule of thumb that 3 epochs generally works. And we will continue training in the normal way. That is, we have the input I, we will get the token, and that will be into the next, and that keeps on uh, going, right? And in the encoder, this is what how a decoder model works. In the decoder part of encoder model, there is a slight variation. There will be something called cross attention will be used. For example, whatever we have especially this is typically used in translation kind of a service or mechanism, you can say. Let's say if you wanted to translate something in English to Kannada, or something in Kannada to English, or vice versa. So for example, in the my, right now we have concentrated or given attention to previous tokens which are generated through the decoder, right? In the decoder part of encoder decoder, the k and v values would come from the encoder block, and that is the major difference between these two. So cross encoders, of course, again thanks to Karpati for a brilliant explanation. Whenever the key and values are come from the different distribution, in this case I think this is that coming from the decoder, and in the encoder it will be coming from the encoder block, right? That's where we call it as a cross attention, but more or less the mechanism would remain the same. In this case, k and v values are decoder only in this model, or coming from the generated tokens of the decoder. But in the encoder decoder model, k and v values would come from the last layer of the encoder model. and that's what make the differentiation between these two things. So now, uh, as I think I was saying in the initial that why did we do this divided by square root of dimension, right? For example, in bird, if you take it, the head dimension head is typically 64, and we will multiply q and k, and will be divided by the square root of 64. When I read the paper, I think I was not sure it is mentioned, not specific reason as such mentioned in the paper, but I think I just going through the Kapati video and he has explained this brilliantly, and I'll go through the screenshot. For example, I've just taken a torch, and the version I'm using is 1.13. Doesn't matter whichever the version you're using here, and I'm setting somebody to like 1999. And I was saying I just taken the BERT example because whatever I'm going to implement here, it is nothing to do with the decoder block, but this is the explanation of why we should divide by square root of d. Of course, there are many papers mentioning that divided by square root of d actually is won't help, right? That's a separate discussion. Let's say in the if you are going with this bird and it has several layers, and each of the layers has 8 heads, and each of the heads dimension is 64, and I've just taken it, and I just taken q and k as randomly. That means how you can read this as it has one batch having 32 tokens, and each of the tokens is having 64 dimensions. Okay, and we know that it's a scalar product, that's why we need to keep it as both number of tokens and head size as same. And if you see the mean and variance of this generated query and queue, of course it is not generated, I just generated it through the random. Variance is 1, and mean of this is almost 0. Even the variance is 1, right? And now if you want to multiply these two, of course, right, it is a q into, we will transpose the k accordingly, and then we will multiply it, it's a scalar multiplication, then we will get the size of 32 cross 32. It's like order of n square. We have also discussed this, why it is order of n square and how it affect the computational, etc., etc., while we're discussing in flash attention. So what does that mean? Each of the tokens, that is 32 and 32, will give importance to the rest of the 32. That's what you can verbally read it as, right? Let's try to check the attention weights of the calculated. If you see it, it is 67. Okay, and we have the k vector, we have the q vector whose variance is almost 1, but when you take the dot product, the variance is not 1, and it is almost at the scale of the head dimensions, which is 64, right? That is the reason why we should go ahead and divide by the square root of d. And when you divide by square root of a d and when you check the variance, it is almost 1, right? And if we don't divide by square root of d, that is the dimensions, then the variance will be too much, right? So what, let the variance be too much and let it not be 1, but how does it affect, right? So when you say for any distribution, I think when you say the variance is high, the numbers coming from a distribution will be like far away from each other. It could so happen that in the attention, if we, because after this definitely we're gonna attend the softmax, that is what we discussed here, right? And softmax, sorry, here. And when you apply here, it might happen that a token in a given input, it might end up with giving the attention for only one of the words. Let's say we have 5 in this case. Let's take an example of this, right? Let's say we have this I love, right? We don't want the word my to have an attention only on the word love. It should also give some attention to I, right? And you should also give some attention to love. Similarly, you should also give some attention to my, whether we ignore it while computing it. Similarly, here, if we go ahead without doing this divided by the of the square root of the dimensions, it might so happen that each of the token will end up with giving the concentrate on only one tokens, and that we don't want. When it is normalized, we are giving a chance for each of the token to have an attend to rest of the tokens an equal amount of time or equal amount of computation. So in short, it will be biased, and when we have divided by, it won't be biased, right? And to understand further on this, just check the Karpati's video, that will help you to understand. So by saying this, I'm going to end here. We will study next set of LLM jargons, something like MQA, GQA, KV cache, page attention, etc. In the next video. Thank you so much.